going to do is we are going to do our best to, I say we're going to do our best in immediate laughter. It's very concerning. We're going to do our best to tie up everything that we know about f of x, f prime of x, f double prime of x, as far as they relate to all these different things and how they tie together. And then what we're going to do is we're going to move on and practice all these things, okay? So we're going to make a chart. You're going to do your best to make this chart organized. This chart is going to be written on this sheet of paper, and then you are going to do a smaller version of this chart on your cheat sheet, okay? Because you want all this information on your cheat sheet to refer to, okay? So 3 columns. I don't know if you want to fold your paper to make these columns neat or like how you want to do it. I know that Cooper's going to like he already has his paper like this. I can guarantee you his holes are on the right side. Oh, they're not. They're not. Cooper, you are making improvements. And then when Cooper does his 3 columns, I know they're just going to be like this, 3 columns like that. Cooper, is that how your columns are already? I just know. It is bullying, but it's accurate bullying. Is it still bullying if it's accurate? I don't know. Does it? Okay, that's fair. So you can, I don't know if you want to make them like somewhat even or whatever. So I'll show you just kind of what mine looks like. This is what we're going to eventually do. Something like this. Okay. So the first column is f of x. This is the function. The second column is f prime of x. That's the first derivative. And then f double prime of x. That is the second derivative. So what we're going to do is we're just going to tie all this stuff together. Okay, we're just going to make sure that we know exactly how all these things relate to each other, and try to see if we can make that big picture perspective happen. Okay, so when you take f prime of x and you, actually we'll go back, we'll say when you're looking at the original function and you want to know where the relative extrema are, you want to know where the relative extrema are, So as I was saying before I was so rudely interrupted, if we are looking for relative extrema on the original graph, then if we had a picture of the derivative, so they didn't give us a picture of the original function, they gave us a graph of the derivative, what would that look like for a graph of the derivative? It'd be the x-intercepts, okay? So these would be x-intercepts, okay? Or what else could it be? So, because x-intercepts would be where f of x, or f prime of x equals 0, right? So a whole, what else? Vertical asymptote, okay, so we're thinking x-intercepts, or we're thinking places where it's undefined, so places that are a little bit weird maybe. So we're thinking vertical asymptotes for sure, but places of kind of some weirdness, because that is where f prime of x is undefined, okay? So here, these are our critical points. X-intercepts, vertical asymptotes. And so when we are looking for this, if we were doing an FRQ, our justification If we were doing this, we wouldn't say, oh, it's an x-intercept on the graph. Oh, it's a vertical asymptote on the graph, and that's how I knew. I'm never going to say the graph. That is bad justification. It's vague. I'm going to say f prime of x was equal to 0, or I'm going to say f prime of x was undefined. Okay? That's my justification. That is calculus. Does that make sense? Because I mentioned a derivative. The derivative is 0. The derivative is undefined. I'm even using the name of the function. F prime of x is 0. F prime of x is undefined. So I'm not being vague at all. I'm saying who, the derivative. I'm saying what equals 0 or is undefined. That's why it's good justification. Does that make sense? Okay. All right, and then we know nothing about the second derivative. Oh, are you back? You're back right now to finish it? I hid it from myself. There was a stack. Nate, and I put it somewhere, and I hid it from. Is it over there? Are there tests over there? I think I. All right. Now I put an x. Derivative, because the second derivative, it tells us something about the relative extrema. Oh shoot, I just realized that I could have done a better job about, hold on. There's an answer to this. I did not include when I've done this. I've done this every year and I've never included, this is the first derivative test, right? I've never included the second derivative test on this. You guys. Okay, so let's do a better job with this. So let's say relative extrema. Let's be a little bit more specific. So we have a relative max. Let's fix our justification. Let's do a slightly better job because I just realized my mistake when I put an x in there. Actually, no, hold on. Okay, draw a line, sorry. No, this is good. Okay, relative max. I'm so sorry. This is classic example, you guys. Classic example of why you should be working in pencil. Is everyone working in pencil? This was very intentional. I was just making a lesson here of why we should be working in pencil. You're welcome. Okay. Underline justification. Whenever you have a relative max, here is your justification that is appropriate for writing on an FRQ. Okay? You can say something like f prime switched from, what are the signs on the sign chart to show a relative max? Positive to negative. So you can say f prime switched from positive to negative. F prime switched from positive to negative. You could say f prime was greater than 0 and then f prime was less than 0. Does that make sense? F prime was greater than 0 and then f prime was less than 0. Okay, so you can say it like that. You can say f prime okay. So see how I'm saying what, or who, I guess, who, f prime, and I'm saying what, greater than 0, then less than 0. I'm using the ideas of a sign chart, but I'm not drawing a sign chart. I'm not referencing a sign chart. I'm not saying the sign chart went from plus to minus. But in my head, that's what I'm doing. Does that make sense? Okay. All right. So relative max. I'm not going to write relative min. I'm just going to say we know relative min. Should we write relative min? No, we're okay. We can make the assumption. Okay. Okay, so over here with the second derivative, we're going to go ahead and write the second derivative test. So we're going to say, with the second derivative, our justification for the relative extrema, we're going to say relative max. And then how do we know that a critical point has given us a relative max? How do we know that one of these critical points has given us a relative max? So f prime of x equals 0, where where the second derivative, so it's where the second derivative, and it has to be, hold on, it has to be concave down, so the second derivative is less than 0. Okay? And in parentheses, I'm going to write concave down. So if you can show that the second derivative has given you that it's concave down, where the critical point is, that means that you have a relative maximum. Does that make sense? That's your second derivative test. So if it's concave down, you have a relative maximum, right? So we don't do second derivative tests very often, but if we do it, it tells us about our relative extrema. Relative maximum, or minimum, I mean, if your critical point happens where the second derivative is greater than 0, where it's concave up, that's where you have a minimum. Okay? So that's how you can relative extrema. It's kind of the first derivative and the second derivative working together. Does that make sense? First derivative, second derivative working together. So it's where the critical point, f prime of x equals 0, it's where the second derivative is greater than 0, if the second derivative is positive. Does that make sense? So again, these are the bigger thing here are justifications. Those are calculus justifications. We cannot say the word sign chart. We cannot say the words the graph. The only appropriate justifications for FRQs are these words: f prime of x equals 0, f double prime of x is less than 0, f double prime of x is greater than 0. So whenever you use justification, or say who, which is the function, the first derivative, the second derivative, and you can say that. You can say derivative. You can say the second derivative, or you can say f prime, f double prime. They will even let you misname it. So if the function is talking about, you're doing g in the problem and you call it f on axis, they will still give you points. As long as you don't call it the graph, and as long as you don't say it, because it is vague. Are you saying it, the function, or the derivative? We don't know because you used it. Does that make sense? Okay. All right, so there's the first part of our chart. Let's do the second part. It's going to go faster after a second, I promise, because I made most of my points on that. All right, so the next one is increasing. How do you know that the original function is increasing? By looking at the graph of the first derivative. It is above the x-axis. It has positive outputs on the sign chart. It is above the x-axis. Okay, so when you, yeah, absolutely. So when you look at that graph, see that it's positive, you're going to see that it's above the x-axis. We cannot use those descriptions. That's not calculus, that's intuitive. Those are intuitive descriptions. So our justification here, pull to the left. All the strings all together, put all the strings in one hand, and hold them to the left. And nice. Yay! All right. So here, increasing intervals, they are positive outputs. They're above the x-axis. If we look at this on our sign chart, this is a plus on our sign chart. In the picture of the graph, it's going to be above the x-axis. But the justification that we are going to write is we are going to say f prime of x is greater than 0, or we're going to say f prime of x is positive. So you can say f prime of x is greater than 0, or you can say f prime of x is positive. Okay, so you say who, f prime of x, and you say what is positive. Okay, those are good justifications. All right, we don't see anything for that in the second derivative. Next one is decreasing. how do we know that the original function is decreasing? Hello. Oh, that's so fun. I will keep working here. I don't know why I say these things. All right, decreasing. So what do we see about the derivative? If we look at the graph of the derivative, what are we going to see if we know that the function is decreasing? Negative output, or it's below the x-axis. And then what type of justification are we going to write on an FRQ? Of x is less than 0. They're looking out there. That Miss Rice is so fun. What a great sense of humor. All right. Next, how do we know, we're going to start over here with the second derivative first. How do we know that the function has a point of inflection? Yeah, the second derivative equals 0. So the second derivative is going to have an x-intercept, or it could be undefined. It could have a vertical asymptote or something strange where it is undefined. So typically vertical asymptote. It could have a hole of some sort. So I'm gonna write maybe write undefined weirdness. Is that good? And let's go back up to VA. Let's go back up here and write that up here as well. Undefined weirdness. Although I will say this is not nearly as common. Typically, you're going to find those just as x-intercepts. Honestly, I do not typically see them as anything other than x-intercepts. But it could be something else. It could be a vertical asymptote or something else. Okay, so x-intercept, something where it's undefined. Okay, so our justification here is what? Okay, f double prime of x equals 0. Okay, and then we have to be careful too because we know that it doesn't always happen at the x-intercepts, and we should write a little note on the other one too, right? It doesn't always happen at the x-intercepts. What has to be the case for it to actually be a point of inflection? Because we know sometimes we would find a point of inflection, but it wasn't actually one, right? What has to happen? It has to change signs, okay? And I've seen students say there's a point of inflection and they're wrong because it was negative to negative or positive to positive, okay? So the nice thing about points of inflection is you don't really have to specify, oh, it went from positive to negative, it went from negative to positive. So up here we have to say what it did, and let's write a little note to ourselves. These ones, the nice thing about these is that critical points, it's a critical point if it equals 0, no matter what, it's considered a critical point. It doesn't have to switch signs to be a critical point. If it equals 0, it is a critical point, okay? And then for us to go further to say if the critical point is a max or a min, to do the sign switch, and I think all of us are pretty comfortable with that. The place where I've noticed that students make the mistakes is they say, okay, this one equals 0, it's a point of inflection, and then sometimes I'm like, well, it didn't switch signs, so it's not a point of inflection, okay? So let's write here equals 0 and switches signs, okay? So f double prime of x equals 0 and f double prime of x switches signs. Positive to negative, negative to positive. Okay? It's kind of like the idea, you guys know how when we do the position, velocity, acceleration problems, and you can say the speed is decreasing because the signs are opposite. It's like, as long as the signs are opposite, you're good. It doesn't matter if the velocity is positive and the acceleration is negative, or the velocity is negative and the acceleration is positive. As long as they are opposites, you're good. So you don't have to specify which is which. As long as you say they're opposite signs, you are fine. So as long as you say they switch signs, you have a point of inflection. But if the signs are the same, you don't. So when we say our justification here, not only does it equal 0, they have to switch signs for it to be a point of inflection. Okay, now, so this is what it looks like on a second derivative graph, but it actually looks like something on a first derivative graph too. So what we have to do is we kind of think of this as like, okay, if this is the second derivative and this is the first derivative, what, if we think of this, the second derivative is actually just the derivative of the first derivative, right? So if we go back and we can take this and kind of shift it up and think of it as just this up here, does that make sense? Okay, so if that's the case, that means that this is just, these are relative extrema, right? So if we were to look at the first derivative graph, then the places we could predict where the points of inflection would be, because on the first derivative graph, they would show up as relative extrema, right? They would show up as places on the first derivative graph where the first derivative would have a slope of 0. Does that make sense? So the first derivative graph would have a slope of 0. So where this graph has slope of 0 or undefined. So it could be a nice smooth curve, slope of 0, or it could be, you know, those sharp corners, those cusps. But your relative extrema for your first derivative are going to end up being those points where you have those x-intercepts. Does that make sense? So that's how we're seeing these two things giving us the same answer over here at those points of inflection. That's where we're seeing that connection happen. Okay, how are your brains? Brains are good? Brains feel right? Okay, so what is our justification here? Not f prime of x equals 0. So you would literally say f of x has a slope of 0. So I wrote where this graph, but we wouldn't say this graph. F prime of x has slope of 0. Define slope. So you just specifically have to say slope of 0. All right, next one. Okay, concave. We are almost done. Concave up, what does that look like for the second derivative graph? It is positive, so it's going to be a positive output on the sign chart. Okay, so it's a positive output on the sign chart. And then what does it look like on the graph? It's above the x-axis. Okay, and so what's our justification? Is above 0 or f double prime of x is positive. And then, so if this is positive, this is above the x-axis, then what does that look like on the first derivative graph? The slope is positive, or it's an increasing portion of the first derivative graph, so it's increasing. And so our justification here is we could say f prime of x is increasing, or we could say f prime of x is greater than 0, not greater than 0, is positive slope. Okay, does that make sense? Okay, and then the last part of this chart, concave down. So look at the graph of the second derivative when the derivative, how do we know that the function is concave down? Negative outputs, which means that our values are below the x-axis, the points are below the x-axis, and our justification for an FRQ, f double prime of x is less than 0, or we could say f double prime of x is negative. And then what does that look like on the first derivative graph? It's decreasing. And then what justification do we write there? Or we could say f prime. So really, the right way to write this, the name of the function, you say either the function, the first derivative, the second derivative. You can write the name in notation, or you can write the word function, the word first derivative, the word second derivative. And then you say that it's equaling 0, that it's positive, that it's negative, or something of that sort. Okay, so we're just very specific when we do it. And as long as we do that, as long as we don't say the word it, as long as we don't say the word graph, as long as we're not referring to sign charts, then we'll be good. We'll get those justification points. Okay, but when they say justify, these are the types of words and descriptions that they're talking about. Does that make sense? Okay, so now we're going to play a matching game. Where you guys are going to match a description with a function with a first derivative with a second derivative. Whew. Whew.